Okay, so welcome to today's lecture on CMOS MEMS. We are starting with the chapter 5, thermal sensors, and it appears that VGA is the new HDMI. It works stably. The screen is a bit smaller than it uses to be, but we'll do the best. So thermal sensors encompasses a whole range of devices that I would like to address. Among those are temperature sensors, radiation sensors of several kinds, pressure sensors, thermal converters, and flow sensors. And in order to start with these devices, I would like to start with some fundamentals, recalling some physics that you may know, or some engineering concepts that you may know, and that will set the scene for the detailed developments of the individual sensor types. So, of course, thermal measurements are important. You will see, well, these applications that I mentioned in detail, but usually they rely on some temperature-dependent property, something that may vary with temperature, and you know many things that vary with temperature, such as the dimension through the thermal expansion, optical properties, by the fact that the refractive index is a function of temperature, thermal conductivity depends on temperature, dielectric constant, magnetization, and so on. So temperature can be measured directly by measuring one of those properties by using an effect that involves those properties. And measuring temperature itself is interesting because we would like to know the temperature, but temperature changes can be caused by other things, such as modulation of a gas flow, or an incoming radiation, or some other kind of work. Chemical sensors may also cause temperature changes. The reaction enthalpy on the surface causes temperature changes. So temperature changes are important, and we would like to measure them, to measure the broad spectrum of things that are out there in need of being measured. So this is what happens very often. And of course, in particular, thermal devices are also temperature dependent. And we appreciate them strongly because we know how to build them into systems in order to get some signal out. It's not a complicated optomechano whatever setup that ultimately provides the temperature changes. It's maybe just a resistance measurement, very easy thing to do. You need a current source and a voltage measurement, voltage measurement instrumentation in order to determine a resistance. And if you would like to implement a bridge, then it's even easier. And then diodes are also temperature dependent. You know the diode characteristic with the saturation current, and then actually usually exponential -1. Here it's just reversed, but it's equivalent, of course, and depending on the sign of IS. Am I recording now? Actually, yes, I am. Okay, yes, and then in some cases, actually, instead of applying some power source, some current source, which requires intricate circuitry and dissipates power by itself, some effects translate temperature differences or temperature changes immediately without any further effort. And the Seebeck effect, the thermoelectric effect, or thermal power, this is also called, is one of those effects. So if you have a thermoelectric couple, a thermocouple made of two materials, and their respective contacts are at different temperatures, we'll see how that works. There is a temperature difference delta T, then via the Seebeck coefficient, this delta T translates into a delta V, a voltage difference, without any further ado. Very convenient. And you can feed that into a voltage measuring piece of instrumentation system so that you can amplify it and filter it and so on. So it's and also it's an offset-free signal. If delta t is 0, then the output is 0. So very convenient also for designing sensors because you don't have to subtract any offset by some reference device or something. So let me just go into this, these thermal phenomena. I summarize them here in heat transfer mechanisms because they are essential in the operation and limiting also of the performance of thermal sensors. And I'll go through those now one after the other. So, of course, you know about thermal conduction. Thermal conduction or heat conduction is an absolutely fundamental phenomenon. In all those devices, you always have materials involved, and then pieces of the sensor, parts of the sensor are hotter than other parts. And so this is symbolized by this very generic block of material that is kind of lighter red, hotter, and darker red, less hot on the other side. And so there is a thermal gradient. If I translate this color, I would say, okay, there's a thermal gradient. Yeah, why not yellow? That's okay. Gradient of T, a gradient of T that shows in this direction, yeah, from the colder to the hotter. It's a vectorial quantity that shows from cold to hot. And this thermal gradient, when multiplied by kappa, the thermal conductivity of the material, causes a heat flow density actually, or heat flux. J, H, so usually J was a flux, namely charge flux. In other sensors, now it has an index H, which means heat current density. This heat current density has the units of watt per square meter. So if I draw a cross section here, and let's say, okay, this is area A, and I record the heat flow that goes through here, the watts that cross this area, and I divide by the area, I get JH. Now this is called Fourier's law, and it involves, on the one hand, a thermal condition, and on the other side, a material property. So if I translate that into a cuboid, the thermal power that goes through this cuboid can maybe be represented differently. So let's think this cuboid has length L. That was not so nicely drawn. Let me do that again. So where am I? Down here. So there is a length L, and then there is a width. I call that here, well, let's call it W for width, and then we have also H, and A is equal, of course, equal to H times W. And so if I multiply the heat flux density by the cross-sectional area, these square meters multiplied by the watt per square meters, then of course I get out the watt that flow. And so this is minus kappa. So this object is called kappa. Did I write that somewhere explicitly? You're not all Greek, so it may be good to write it down. It's called kappa. This kappa, and it looks a bit like a small capital K, yeah. But when you look up the fonts, there's some little serifs and so on that need to be added for it. Sometimes people write it like this, so you have all kinds of variants. And so that's quite easy. And a gradient of T, what is gradient of T? It's the difference in temperature divided by length. So if we have here a temperature T0 and here a temperature T0 plus delta T, this part is maybe hotter if delta T is positive than here, and the gradient is of course d now in a one-dimensional setting, dt over dx, or if you would like to write this as a difference quotient, it's delta t over delta x. And the equality is true if this is a linear function, if temperature is indeed a linear function, and then this delta x is of course the length over which delta t changes, or temperature changes by delta t. So delta t over L, and then we have kappa A over L times delta t. Now let me just write this down in a little different form. Yeah, I can also write down this as delta t is equal to, and then I write pH all at the end, and then I write 1 over kappa L over A. When you look at this, and you know that this is the thermal conductivity. And if you now think just for a moment in terms of electrical properties, if this was the electrical conductivity, we would write 1 over sigma. And then we would have L over A. We could also write this as rho. The inverse of the electrical conductivity is the specific resistance, the resistivity, rho, times L over A. And so this is what we usually call the resistance of a block of material, a resistive block of material. So indeed, this object here is a thermal resistance, heat resistance. And it connects, what does R, the electrical R, do? It connects the electrical current with some delta voltage, delta U, applied voltage. So delta U is equal to R times I. And here we write delta T is equal to thermal resistance times heat flow. I is the charge flow and P is the heat flow. So there is a one-to-one analogy between electrical phenomena and thermal phenomena. And when you look at this equation here, it's also identical to an electrical equation, because if U is taken, the role of U is taken over by T. U is the electrical potential. T is the thermal potential. So here we have gradient of T. In electrically, we would write this as gradient of U, or gradient of phi, or sometimes, different nomenclatures are used. And if I write the minus here, I have kappa times minus gradient U, or electrically sigma, and this is sigma times electrical field. The gradient minus the gradient of the electrical potential is the electric field. So this is all, the analogy goes to the end. And therefore, if we know how to solve an electrical conduction problem, we also know how to solve a thermal conduction problem. So heat conduction in general, let's continue. Let's continue in 3D. So now I defined some notions. Heat can be generated locally. It is generated locally. If we let a current flow through a resistive material, there is heat dissipation. Heat dissipation that causes the object to become hotter. An incandescent filament works by that principle. You don't even know anymore what that is, because you have grown up in the area of light-emitting diodes, and they don't get hot because they're efficient. But I mean, getting something to be hot so that it radiates was the method that I grew up with, and I have burnt my fingers many times in my life, experiencing ohmic resistance. But of course, I know that you have also grown up with incandescent light bulbs. I'm just joking a little bit. Yeah, the next generation professor will make that joke appropriately. What is this heat generation density? That is the amount of watt per cubic meter that is generated somewhere. And if this is generated somewhere, what can it do? yeah, it can either heat up an object or it can flow away. Yeah, so this is how heat is dissipated, by increasing the temperature or by causing a temperature gradient that then causes the flow that we have just described before, and then the heat flows away. Yeah, so what about this heating up? It requires a property, namely the heat capacity, or I should rather write here the specific heat. Specific heat capacity is also called sometimes. It's the joule that are needed for a cubic meter of material to be heated up by 1 Kelvin. How many joule do I need per cubic meter per Kelvin of temperature increase? And this number that is now written just with a C here is of the order, for many materials, of the order of 10 to 6 joule per cubic meter per Kelvin. So that's kind of not a natural constant, because it has a prefactor in front that can be 1 or 2 or 3, but it's never 10 to the 7 or 10 to the 8 or 10 to the 2 or so. It's always around, for solid materials, it's around this value of megajoule per cubic meter per Kelvin. Very handy to know for some estimates. Okay, then heat conservation says that the heat generated in a location, in a volume, either flows out of that volume or increases its temperature. Yeah? And that is denoted by this heat equation that is down here. And as we go down, we will use the Laplace operator. Now, the Laplace operator is the divergence of whatever function we have here. Let me write an arbitrary function of x, y, and z. Yeah, this is the gradient of the function, and if this causes a vectorial function to be generated, and we can then take the divergence of that vectorial function, and the divergence of the gradient of f can also be summarized, or is usually summarized, as the Laplace operator acting on f. And when you remember that gradient is well, the derivative with respect to x, y, and z, and then you do that here in front, and then you have this dot product, this inner product. Then of course the first one will be squared, then the square of the second one and the square of the third one will be added together, and that's exactly what is written here, the sum of the second derivatives. So now let's assume we have a temperature distribution that is spatially dependent and time dependent. So we can take a time derivative, and we can also take a spatial derivative, the gradient. So that's down here. So let's look at what this first equation says. It says that the heat generated per volume, the watt generated, the joule per second, the power generated per cubic meter per volume, is equal to what is kept locally in terms of an increase of temperature, because increasing the temperature of an object needs some energy, and that energy is quantified by the change of temperature. So I can, again, I could write this differential here as this derivative as a difference quotient. Yeah, so the change of the temperature per time multiplied by C. Yeah, so this kind of looks like this object, and this C times delta T is the change of the inner energy. Change of the energy of the object, and if that is invested by per time, we see that part of that pH is invested in internal energy of the material. The material stands here, and the rate at which the temperature changes is here. But then there is another way of getting rid, for the object to get rid of this heat, this heat power. It is by letting it flow away, by having a divergence. If heat flows away in opposite directions, then locally some heat is lost. So the cause, draw a little object here, and I know that pH is invested here, and I observe that heat flows out here and flows out here and nowhere else because it's isolated, then I know this object is losing energy, and that energy lost through the boundaries is refilled by the generation pH, whatever it is. It might be radioactive atoms that like in the satellites that drift through space. They have these atomic piles or atomic batteries, some radioactive materials that heat up an object, and then there are thermoelectric converters that transform this temperature difference between the radioactive material and then the cold space somewhere on the other side into a voltage, into a little power that can be used by the circuitry, so that this can send some information from time to time and say, I'm still out there in space and I observe nothing except that the Kuiper's belt is really empty. So and if the object was isolated all around, no heat could be dissipated. There would be no divergence of heat. And so if we have this other object with pH and heat is stuck there, then it must become hotter. C times dt over dt. Now, in reality, both effects are always concurrent, and therefore we have a usually complicated problem to solve, a differential equation. So if I replace JH by what we just saw before, namely kappa gradient of T, I will obtain an equation that looks like this. That is a differential equation for temperature. And it has time derivatives, it has spatial derivatives, it has kappa, it has maybe a heat source that is defined. And then we can solve for T, and ultimately we know how the sensor operates. That's a complicated problem. So especially if there is a time dependence. In the stationary case, so let's say if we switch on some heat or some thermal radiation impinges on our sensor, and after a while, it will have heated up, and then it will be heated up enough so that there is a temperature gradient, so that whatever additional heat is absorbed is now conducted away, but that temperature difference is now constant. That is a stationary temperature difference, and that stationary case is governed then by dropping this first term that doesn't change anymore, and by keeping the rest, which is just the divergence of kappa gradient T is equal to minus pH. So we only have a spatial differential equation, and if kappa is assumed to be constant, a number independent of space, independent of temperature, then we can take it out of this. And then we have divergence of gradient. And that divergence of gradient is of course then this Laplace operator. And the kappa that is assumed to be independent of temperature and therefore independent of space. If this object is inhomogeneously hot, kappa could be a function of temperature and therefore a function of location. We assume it to be kappa 0, we have it out there. And then we have a yet simpler equation that is called Poisson's equation. And for that, standard solutions are available. Finite elements do that a lot. And let me just point out that we have to drop the explicit temperature time dependence here. It's no longer time dependent. It's stationary. Now this is also so stationary is here, but is also stationary here. Okay, so that is an equation that is worthwhile knowing. Yeah? Very often we have, instead of having three-dimensional problems, we can simplify problems into one-dimensional form. Yeah? And then everything becomes very simple. If we have two dimensions, then things get a little bit easier, but not fundamentally simpler. Why should we consider two-dimensional structures? Because, and I can just guess. For instance, here you have a thermoelectric radiation sensor. It consists of two thin membranes. Those two thin membranes, left and right, are composed of the dielectric materials of a CMOS processor that was used to fabricate the structure. Those dielectric materials are field oxide, intermetal oxide, or contact oxide, intermetal oxide, passivation for a two-metal process. Maybe 5 micrometer thick. And in between those, there are some thermopiles made of polysilicon, aluminum, and not much else. So there is maybe 6 micrometer thickness of material, but that structure, this chip is 5 millimeter large. So you may have something like a millimeter of membrane, 1,000 micrometers, 6 micrometer thin. That's very flat. It's like a sheet of paper. Yeah? And this sheet of paper, of glass, this thin sheet of glass absorbs heat from outside and gets hotter in the center. It is supported on the edges. The chip is at temperature T0, but because the membrane heats up, in the center it will be hotter, and then heat will flow away towards the suspension, the chip, so that heat goes away, and the temperature increase under this absorbed heat is what we measure. And the phenomena that goes in this membrane is two-dimensional. There is no net third dimension that needs to be respected. And that's why it's worth also in many of these thermal microsensors, especially CMOS microsensors, to consider the special case of 2D heat transport. It looks like the 3D heat transport, but we replace a few things. So for instance, what we had as kappa before is replaced by kappa times D. D is the thickness. If it's a homogeneous material, we have the thickness of that material. We have the kappa of that material. So let me draw this now. This conductive thin material in which the temperature is observed as a function of x and y. And z is as inexistent because it's all kind of happening within this thickness d. And this material is supposed to have thermal conductance kappa. And so the object that plays a role is kappa times d. It's actually the line thermal conductivity. It's watt per Kelvin. Kappa has units, watt per meter per Kelvin. And if it's multiplied by meters, then watt per Kelvin is the unit of kappa 2D. And then heat capacity is also no longer an object that has the appropriate heat capacity or specific heat, no longer an object that has units joule per cubic meter per Kelvin, but you can then say, we have some area and it's joule per area of that material per Kelvin because the thickness is given anyway. And then also heat generation or heat loss density is now written as G, as the volumetric thing that happens here per volume integrated over the thickness, or if it's homogeneous, it's just pH times D, and then it has units watt per square meter. So you can imagine that this thin thing this thin object is really flattened to a mathematical plane, and then it has a property of heat dissipation per area, it has a heat capacity per area, it has a heat conduction that has something to do only with this 2D flow, and the nabla operator, this gradient operator, is a 2D operator with only two derivatives, because the third dimension doesn't exist, and the Laplace operator in 2D is just the sum of those two second derivatives. And then the equations of before can be just translated by replacing all the object we had before, the 2D C and temperature change per time, the 2D gradient here, or divergence operator acting on this thermal flux density in 2D is equal to the heat generation density in 2D. And then the stationary case is just the second term here. And then the case for constant kappa is then the 2D Laplace acting on T. Now you could of course think, what is it in 1D? Yeah. Yeah, I'll let you do that. Very simple. Yeah, probably we'll have a second derivative in one dimension down here. And if I say, oh, this thing is now only a 1D thing. Yeah, it's a very, very thin kind of a conductive wire or beam. And there is no change in this y direction. There's only x that is relevant here. Then probably we can supplement this kappa d by another dimension in this other perpendicular dimension. We can do the same for C. We can do the same for G. And then G becomes the watt per length, and the heat capacity becomes joule per length of that beam per Kelvin, and the Laplace operator becomes just the second derivative. The gradient is gradient, and then well, the divergence is just the first derivative acting on this, and so this is this should be quite easy. And then we have a 1D differential equation with a second derivative that is very easy to solve in many cases. So now often materials are not composed of only one material with one thickness, but they're composed of different constituents. What you have here is an excerpt of a thermopile, a CMOS thermopile. So you have the field oxide down here. Let me write this down. This could be the field oxide. We have here some polysilicon. Then we have the contact oxide that covers the polysilicon. Those polysilicon structures are not just a little cross section; they are long lines that go along the structure, and then there are above the contact oxide there is a metal 1, for instance, metal 1 line, and that's again a line that goes right from front to the back of the structure. So we really see a cross section that we would see at any place where we would cut the structure. And then there's the intermetal dielectric, IMD, and there is obviously in this design, there is no second metal, and then we have the passivation. So we're back to chapter 2, basic technologies. And this whole thing is maybe 6 micrometers or so, order of magnitude, 5, 6 micrometers. And so now the question is, can we describe the thermal conduction property or thermal resistance property of this compound object easily? And that's quite simple. So let's assume of course, there might be now a temperature gradient perpendicular to these structures, or there might alternatively be a thermal gradient along those structures. And that direction along is the easier one. It says lengths, which means in English along. And quer doesn't mean, well, it means kind of at orthogonal angles. So what we had as Christopher Street Day, queer, it is a bit opposite to the convention. And so here we have a perpendicular. No? And so let's analyze the longitudinal case first. Now that's easier because you see, if we have this delta t, yeah, now we know that of course the power that is flowing along a structure, yeah, multiplied by the thermal resistance, that gives the delta T needed to drive that, or corresponding to that heat power. Yeah? If this RTH is replaced by L over kappa over A, yeah? Refer to 3 or so slides earlier. Yeah? That's what we obtained. Read the other way around, as we had it there originally, it said that the pH, yeah, is equal to kappa times cross-section divided by L. That L came from the gradient of T, and now we have delta T. So this combination of material property and geometry is called the thermal conductance, G. And of course, the thermal resistance is just the inverse of the thermal conductance. So if I consider this structure now in the longitudinal direction, I have these different materials all exposed to the same delta T of this per length, but they have different kappas and they have different cross sections. So the flow through the entire structure, through all the material, is of course a sum of the heat flow through the individual material constituents added up. That's the total heat flow. So if I look at the longitudinal case, I think this will be dealt here. Yeah, so I'll just prepare that. Longitudinal, yeah, the G thermal is equal to the sum of the individual materials. I can put an I here, and then there is, it goes over all the materials. So there is field oxide. The thermal conductance of the field oxide will be easy to calculate. It's going to be kappa of the thermal field oxide times the cross section of the thermal field oxide, which is this cross section here, and the length L. And then for the polysilicon, we just have we have the same length, we have the same, well, we have another kappa, and we have another cross section, which will be smaller than that of the field oxide. But the thermal conduction of polysilicon is much larger, so it will contribute a share amount of thermal conductance. Then we have some other oxides, some passivation, and we have some metal. And this metal has also a small cross section here, but it has a huge thermal conductance. It will probably dominate or contribute a large fraction of the thermal conduction to this sum. So you just list the cross sections of these individual materials, their individual kappas. You calculate these individual kappa I AI. Yeah. So this is kappa I AI, and it's all divided by the same L. And this is the thermal conductance of the overall sandwich in this longitudinal direction. Yeah. So such structures are ubiquitous in CMOS MEMS, in thermal CMOS MEMS. Yeah. You take thermal radiation sensors, you take gas flow sensors as they're manufactured by Sensirion. Those are membrane structures with thermocouples and at some central position, a heat resistor, polysilicon resistor that is used to heat up the structure, and then temperatures are measured upstream and downstream, and large sections of that structure consist of sandwiches like this. So if I go again here for the conduction in the longitudinal direction, we have conductive elements with common length L and individual cross section and individual thermal conductivities. Okay, the index is now N, and GTH is the sum of the individual conductions. And if I need, for some reason, to calculate the thermal resistance of this compound structure, I have parallel conductors, so I can add up the currents flowing through these parallel conductors, like in the electrical analogy. You have parallel resistors. They are parallel conductors. You add up the currents that flow, and the overall resistance of these parallel resistances is not given by the sum of the resistances, it's given by the sum of the inverse resistances. So what is very simply expressed in terms of conductances, namely the additivity of the conductances in this case, translates into the, this well-known law that the resistance of parallel resistors need to be inverted, and then the whole sum needs to be inverted to obtain the resistance. You know that from electrical engineering. Yeah? I'm looking at you. Sorry? You're a mechanical engineer. But you study microsystem engineering. Okay, so let me just show this to you. Yeah, so things that look like this. Yeah, so I have two resistors, R1 and R2, and I'm talking about electrical resistors now. This can be replaced by a single resistor R, whose resistance is calculated as R is equal to 1 over R1 plus 1 over R2 to the, and then inverted. Yeah, it's just like this equation here. 1 over R is equal to the sum of the 1 over R's. Yeah? And in mechanical engineering, these things do also exist. Yeah? If you have mechanically elastic structures, and you have them joined together, the elastic constant adds up. But if they are in series, you cannot just add up the elastic coefficients of these structures. Then you have to do this inversion thing. It's like capacitors and resistors. The capacitors in series need also to be handled by this formula. And so in mechanical engineering, similar formulas exist also. And so that's easy. Now in transverse conduction, it's more difficult. Now, of course, in particular, in such a complicated structure, to calculate the thermal resistance from this side to this side, I would probably recommend to my PhD student to do a finite element simulation, because it's a complicated structure. It has a granularity in the longitudinal direction that is as strong as in the vertical direction. So for heat flowing in this direction, probably heat will flow in here and then out here again. And then some will flow in here, because these are materials that conduct better. And then of course some go in between, and so it's a very complicated heat flow problem that is best handled by finite element simulations. But if you have a situation that, let's say, now I can do a schematic drawing like this that adds, has components in series with different compositions. So let's say this has a material in between, and this has another material at another layer in between. Say the left side has polysilicon in between, and the other element has metal in between. And then maybe we have another piece of material that has nothing in between, just pure oxides. Then to calculate the thermal resistance from here to here, is like adding resistances to each other. Yeah, the resistance from here, this R1, this R2, and this R3 can be added up into the resistance of the overall, the total thermal resistance, as in the electrical regime, because the electrical analogy is really fantastic in this thermal domain. Yeah, so the thermal conductance of such a piecewise separable structure, where we forget about what happens here. You know, I mean, heat might do something complicated here, and then here also it has to spread, and so we forget about these transition effects or edge effects, as they're also called. I would say, yeah, it's well described by these long extended homogeneous structures. Then we can just say, okay, the total thermal resistance is equal to the sum of the individual thermal resistances. And that means that, yeah, how do we calculate these thermal resistances? Of course, that is just 1 over kappa. Yeah. And what do I write here? Yeah. No. Needs to be done. Delete. History has been undone. Yeah. So the thermal resistance of one of those materials can now be considered as a parallel conduction of different materials. Can't it? Yeah. So what we just developed applies to it. The resistance is equal to 1 over the sum of the inverse resistances. So this, what is written here, you find here for each individual resistance. So the mth resistor, m equals 1, 2, 3, has material components that again are numbered from n equals 1 to some maximum. And these expressions that you find here are the inverse resistances, or the conductances. Of course, these are the conductances. You add the conductances and then you invert the total conductance to obtain the resistance of the nth element here in the series. And so this is how you handle this. So this is as much as I would like to say for conduction in solid materials. Now, these solid components are also surrounded by gas. So the membrane has air around, and then gas dissipates heat also by conduction and by convection. And that is again a diverse subject. So hot components are the origin of energy transfer to the gas. And then these gas molecules, these hot gas molecules diffuse and transmit their energy to other gas molecules. And therefore, heat energy is transported through the gas, either by collisions, which would be conduction, or by motion of these gas molecules. If there is motion, then we talk about convection. And so let's not talk about the motion thing, but only about the conduction at the moment. So conduction means stationary gases that have different temperatures at different locations. And now the heat transfer in such gases depends on the length scale. Because a gas molecule will fly for a certain distance before it collides with another gas molecule and changes direction. This is happening 10 to the, I don't know how many times in this lecture hall per second. You can calculate that. The gas molecules here, the nitrogen molecules travel for a distance before they collide. Do you have an idea how far a gas molecule travels before it collides? On average, the mean free path of a gas molecule, what would you guess? Centimeter? Of course, the gas molecule has also speed. We can also talk about the speed. What would you say? Millimeter? You? Micrometer. So you're closest. It's actually at atmospheric pressure, it's 100 nanometer approximately. The order of magnitude of 100 nanometer. Do you know the speed of those gas molecules? I'm sure you know. You have a phenomenon that is a direct manifestation of that speed. The mechanical engineer. Yeah, you have done acoustic engineering. Acoustic engineering. The speed of sound. Do you think the speed of sound could be faster than the speed of the molecules of the air that transmit the sound? Maybe. Yeah, what? Then what? Then the speed of light of an electron. Yeah, because there is a potential. But I mean, you know, the speed of sound is transmitted, or the sound is transmitted by the motion of the molecules, not by some potential that that is somehow subjacent or so. Yeah. So it's duck, 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 yeah, up to your ears that transmits my voice. And therefore, the thermal speed of molecules in air is something like a few hundred meters per second. And so you can imagine how often these molecules collide. Because if they travel 100 nanometers at that speed, they do lots of collisions per second. Yeah. So this length scale, this typical length scale, this mean free path, as it is called, or the collision, the mean free path between collision, lambda col, and the dimension of a structure is determinant about what kind of heat transfer occurs. Here, you know, if I feel the heat of my mobile phone, because I just had some intense video chat, I can feel the heat. The distance is a few centimeters. There is a temperature difference, and the gas molecules transmit the higher temperature by colliding with other molecules, and more energetic molecules collide with colder molecules and transmit their energy, so that finally I feel their collision heat, their kinetic energy coming originally from the mobile phone. And so you imagine these 5 centimeters and the 100 nanometer by reference. Many collisions occur before the heat is transmitted to my hand. And that ratio of the collision distance divided by the typical distance over which heat is transferred, that is a well-known number in the theory of heat transfer. It's called the Knudsen number. Americans say Knudsen number because Kn is pronounced like N, you know. But Knudsen was, I think, a Scandinavian scientist. So Knudsen is this number here, and for typical distances in our macroscopic life, lambda collision over dH, the typical distance between hot and cold components, is lambda is much smaller, so the Knudsen numbers are very small. And then the gas can be considered like a continuum, like a very, you know, how do you say, the opposite of dense, a non-dense, a very thinly populated solid. Sparse, dicht, dense, and then flüchtig, volatile, maybe something. So you can apply in this gas with these many collisions. You can say, oh, it's like a solid that does not conduct very efficiently, but the heat transport equations are the same as if it were a solid. It's just a kappa that is low. Whereas if you imagine now a situation where you have a distance, and actually nanometers scale, and the molecule could actually fly for a large distance, but then it is prevented from doing so by hitting the other component. So here it leaves at temperature 1 and it reaches the solid at temperature 2. Then of course there is no intermediate collision. and then the heat is transferred kind of directly from here to here. Yeah? And whether I make this distance now even a little bit smaller or a bit larger won't make a change, because what happens at the surface is exactly the same. So somehow it becomes independent of this distance. Yeah? This is called the molecular collision regime. Yeah? Molecules, hot molecules come here, heat here, maybe transfer their energy, and then after a while they leave this object again, this colder object at T0, and then they fly back, with little kinetic energy. They go back, and then there they heat up again, and transport heat again from hot to cold, and so heat is also transferred. But this is totally different from this continuum. And the Knudsen number is the number that says which regime we're operating in. So let me just say that in the Knudsen regime of Knudsen numbers much smaller than 1, we have gas. We have usual conduction, continuum conduction, and that means that there we can talk about a heat flux density which is equal to minus kappa of the gas. That is now a property of the gas that is listed in tables and can be estimated by gas kinetic theory times the gradient of T. So this is absolutely fundamental. And in this case, I need to drink. It is interesting that kappa is independent of the density of the gas. Who would have believed that? Do you? If I had said, how does kappa, the thermal conduction of gases, depend on the pressure or on the density of the gas? My natural intuition would be, the denser, the more transfer. There are more molecules, but it's not true, because the molecules that want to transmit their heat from hot to cold, they are also hindered more by the other molecules if the gas is denser. They cannot travel as far, so it's tougher to get the energy across. And that is, very compactly summarized in the fact that the mean free path of these molecules is inversely proportional to the density. But kappa is proportional to the density and proportional to the mean free path. So that's a result of gas kinetic theory. And so this just cancels, and therefore kappa is constant. So if we evacuated this room to, let's say, 90% of or 50% of the density, we could still breathe. We would be like at 5,000 meters, like on Mont Blanc, would be kind of tough. We wouldn't walk very fast and jump around. No, very calm, 50%. But the heat conduction of that gas is still the same. Even on Mount Everest, with reduction by 80%, still the same thermal conduction. And it depends on temperature. So on Mount Everest, the thermal conduction will be lower because the temperature is lower. But if we had some experiment at room temperature on Mount Everest, it would conduct the same. So here is some numbers. Thermal conductivity of air is at 300 Kelvin is 0.026 watt per meter per Kelvin. Well, that's a number that I remember easily, because 0.026 I also encounter in semiconductor physics or other thermal physics, KBT. This is 0.026 milli-electron volts. It has nothing to do with that number. It's just a numerical value that is easy for me to understand, to keep. That's why I know the thermal conductivity of air. Say, this is what I need to. So please don't think that they have anything in common, except the numerical value. How does that compare with solids? So we mentioned polysilicon before. Well, polysilicon has a thermal conductivity of something between 20 and 30 watt per meter and Kelvin. Aluminum has something like 240 watt per meter and Kelvin. Silicon oxide has a thermal conductivity of something like 1.4 watt per meter and Kelvin. So even the material that is the best insulator of the materials of a CMOS process, silicon oxide, 1.4 meter per Kelvin, has way higher thermal conductivity than air. That's why we can insulate ourselves against cold temperatures outside. We put on a sweater of wool. It has these, these many fibers. It has stagnant air. The stagnant air cannot do convection. It can only do conduction. And that conduction is very low. That's why this woolen sweater of half a centimeter is good against even minus temperatures out there, maybe for some time. If we were cladding ourselves in a sheet of 5 millimeters of aluminum, I tell you, you would be freezing pretty rapidly because the thermal conduction would be 240 watt per meter in Kelvin. And the temperature outside, wow, that hits you immediately. There is no temperature gradient in between. So what else do we see here? Colder air conducts less. I think there is some square root of T law in here. I'm not sure exactly. I don't have this ready in my head, but we also see that lighter gases made of lighter molecules conduct more. Hydrogen has a higher thermal conductivity than heavier gases, xenon, for instance, or neon. No, neon is lighter than air. Xenon is heavier. That's why in expensive windows with the double pane glasses, instead of putting air in, they put xenon or argon. Argon is also heavier than, I think, nitrogen. And so that means that we can have better insulation through the air, through the windows. It's a bit expensive, and xenon is rare, so it's better to waste it on, not to waste it on such applications. The ideal thing would be to evacuate. Then you would have air at zero pressure, and that does not conduct. Actually, I need to make a precision. So this law that kappa is constant is only valid as long as the Knudsen number remains smaller than 1. That is essential. If I evacuate the window pane more and more, the mean free path between the molecules becomes larger and larger, and at some point, I would say, it's independent of the density. You said it, So let me evacuate it. Still kappa. No. Now, at some point, lambda collision is larger than the distance between the window panes, and then this generalization does not apply anymore. Okay, and so no air does not conduct. Okay, for sure. Okay, now we also have heat conduction at Knudsen numbers larger than 1. And there is a result from kinetic gas theory, which I have summarized schematically like this. The heat flux density is proportional then to delta T. And it does not depend on the length anymore. The length is not in here. The length The length is here. This is delta T over length. Yeah. So this characteristic length over which the temperature changes by delta T between hot and cold, yeah, is implemented in this formula. Here there is no length. Yeah. There is the density, and then there is some constant, some gas kinetic constant that involves some numerical factor Z, the order of 1, 2, 0.5, something like that. Boltzmann's constant is 1.38 times 10 to the minus 23 joule per Kelvin. Yeah? And then there is the average velocity of the molecules, the flying molecules. Yeah? So let's say at room temperature, a few hundred meter per second, what we have estimated before. And that product is this C here. Yeah? And so I gave KB here, mean velocity. And now how large is this CP? So I have let's say eine Hausnummer, as we say in German, a number to remember that gives a good approximation. Yeah. So at 1 Pascal, C times rho is equal to 1 watt per square meter per Kelvin. So if we had rho smaller, so that's at room temperature, okay? I also need to add. If we had now only 1/10 the pressure, let's say 0.1 Pascal, then rho would be 1/10, and then of course the C times rho is only 0.1 watt per square meter per Kelvin. And that's easy to understand that this goes proportional to the density. The density is equal to the molecules that are currently transferring energy, and if there is only 1/10 available, then only 1/10 of the energy will be transferred between these objects. So now let me think about making this pressure higher: 10 Pascal, 100 Pascal, 1,000 Pascal, 100,000 Pascal. Okay, 100,000 Pascal is 1 atmosphere. It's this pressure here. Oh, and could I just say, okay, then rho is 10, 100,000 times larger? Not in general. I need to know how far this distance is. Yeah? If this distance is 10 nanometer, it's a very small nano gap. Yeah? They have been fabricated. Yeah? And if I fill this with air of atmospheric pressure, the lambda collision is still 100 nanometer. So it's still larger than this length. The Knudsen number is larger than 1. And then this formula applies even at 100,000 Pascal at one atmospheric pressure. And I know the transfer of heat between this cold nanowall and this warm nanowall 10 nanometers apart is going to be 100,000 watt per square meter per Kelvin of temperature difference. Yeah? But if that wall is, they are far apart, 1 centimeter apart, then I cannot just go from 1 Pascal to 100,000 Pascal, because at some point the collision length is going to be smaller than that distance, and then I'm no longer in that regime. Yeah. Let me just estimate at what pressure for 1 centimeter this would break down. So 1 centimeter distance, L equals 1, or we call it DH. Yeah, the distance, the characteristic distance, 1 centimeter. So at what pressure am I no longer in this Knudsen regime? Well, for 10 to the 5 Pascal, I know the collision distance is 100 nanometer. Yeah? I'm just using house numbers. Yeah. So representative numbers. Yeah. So if I If I go down by a factor of 10, I'm at 1 micrometer. Yeah, 1 micrometer. And then from 1 micrometer to centimeter, how much is it? 10 to the 4. Yeah? So from 100 nanometer to 1 centimeter, I have a factor of 10 to the 5. Okay. So it means that at 1 Pascal, the lambda collision, so that is lambda collision, at 1 Pascal, lambda collision is equal to 1 centimeter. Okay, so for hot and cold walls 1 centimeter apart, with 1 Pascal of pressure, I'm just entering that regime between, I'm just at the interface between conduction, continuum conduction, and molecular heat transfer. So probably I need to go to 0.1 Pascal, strongly rarefied gases, in order for this to apply. But if I have a gap of 1 micrometer, 1 micrometer, okay, for 1 atmosphere, lambda collision is smaller, so it's like continuum transfer. But if I go down by 1 power of pressure, or 2 powers of pressure, 0.1% of an atmosphere, then the collision path is 10 micrometers, and that's larger than a 1 micrometer gap. And you will see a Pirani sensor that has a 1 micrometer gap, roughly, and it's sensitive in pressure at this pressure ranges of a fraction of an atmosphere, tenths or hundredths or thousandths of an atmosphere. And that's because we transit from continuum transfer to this molecular heat transfer. And now, of course, the question is, what do I do when I'm not sharply in one or the other regime? How do I mix them? And there is some mixture formula that you can see here, which has the L in form of the typical distance dH in here. It has the continuum kappa here, but it has also the C rho here. And so when preparing for the lecture yesterday, I thought, can we transform this a little bit? So let me divide this by C times rho. Actually, this is rho. Again, like the electrical resistivity, but here it's the density. So let me divide. This is kappa divided by dH plus kappa over C rho times delta T. And I can write this actually as kappa over dH plus lambda collision times times delta T. This object here has the units and the size of the typical lambda collision. So this is now quite easy to see what happens. If lambda collision is much smaller than the physical separation distance between the hot and the cold structures, then so let's say lambda call much smaller than dH. This is equivalent to Knudsen number being much smaller than 1. In this case, this formula becomes kappa over dH times delta T. Okay, we know this. This is delta T over dH, gradient of T times kappa, and then this is equal to the heat flux. And there may be a minus sign that is missing now here. We have to think that heat flows from the hot to the cold. It's the absolute value of the heat flow. And on the other hand, if dH is much smaller than lambda collision, what does that then become? Lambda call much larger than dH. then we are in the regime of Knudsen numbers much larger than 1. And then the formula becomes kappa over dH. Is that correct? Times delta T. Yeah. If this dH becomes much smaller, so now we have I probably better yeah, you have seen that I would probably better have transformed this differently. Yeah, so if this dH is very small, yeah, then this is what remains. Yeah, and then we have kappa over C rho, yeah, which then can be simplified into C rho times delta T. Yeah? So the two limit cases are reconstructed, yeah, in both cases. And in the middle, it's kind of an appropriate mixture. Yeah? You can also view this as a parallel formula. Yeah? 1 over plus 1 over actually gives this result. Yeah? And so if I try to draw some curves here, so what I can draw here, what shall I take as the horizontal? Let me take the no, I'll construct an exercise, you know, for you to produce some graphs that represent this formula. Yeah, that will be more efficient, because now I already did a lot of teaching and my brain starts to hum a little bit. Yeah, so I cannot think as clearly as I probably need to fill this graph. Let me talk about radiative heat transfer for a few minutes. Yeah, so this is also something important because if you have this let's say membrane that is heated by some let's say radiation, then it will become hotter in the center by some delta T with respect to its surrounding. And it is, you know, it is kind of suspended on some silicon chip. The silicon chip has temperature T0, and then here in the center it's hotter, and then heat flows, of course, away from the center, but we have a delta T that is measurable. And that gives us some information about the radiation intensity, for instance. Yeah. However, this object, this hot object, also radiates radiation away. Yeah. This is thermal heat transfer, radiative heat transfer. Anybody transfer heat just by radiation. If we were in vacuum, in outer space, we would cool down quite fast because we are thermal bodies radiating in this law called Stefan Boltzmann law. And I think we would radiate something like 60 watt. Yeah. And that's if we don't feed ourselves, you know, rapidly, and we don't protect ourselves, then we will freeze to death. And that heat transfer is described by this law of Stefan Boltzmann. So let's assume this object to have temperature T. And then now black body radiation is emitted in all kinds of directions. And if we add up this whole power over all directions that radiate away from, let's say, 1 square meter from such a surface, then the power per square meter, is given by this fundamental constant, really fundamental, the Stefan Boltzmann constant. sigma SB. That is not a material property. That is an absolutely fundamental constant. It's the kind of the power radiated by a so-called black body, yeah, and that is given by this epsilon, and the power that is radiated away increases with T to the 4, yeah, the fourth power of temperature. And then this body may have a little property called emissivity. Yeah? It may only emit a fraction, but that's because of its internal construction. Yeah? But that epsilon is going to be of the order of 1, 0.5, 0.2, some fraction of 1, never larger than 1, always smaller than 1. And that is what this body here also emits. So it not only loses energy by conduction through the solid materials or through the gas that is surrounding. There is heat loss through the gas to the bottom, to the upper side, but it also radiates heat away. And the design of thermal sensor always has to think about that phenomenon, whether it's important or not. And larger structures are more sensitive to this radiative heat transfer. Very small structures may not. So this is, there's a very fundamental law due to black body radiation. You know, probably Planck's radiation law that says how much one of those objects radiates as a function of frequency. I should go here. Frequency. Sometimes it is also represented as a function of wavelength, and another curve that looks similar arises, and this is the radiative power U per wavelength or per frequency that is radiated away. And if you integrate this whole thing over all frequencies or over all wavelengths, then you obtain this radiative power. Now, the question of the direction dependence of this radiative power is also important. It's described by so-called Lambert's law. Yeah, so there will be a maximum power perpendicular to this surface element, and as you go sideways, of course, you see this surface element under a stronger and stronger angle, and the apparent area that it fills with respect to your eyes becomes smaller and smaller. And if you are tangential, you don't see it anymore. So the power distribution as a function of the angle, if I say here, if I do a polar plot, so here is 0. So this is the plane of this surface element. In the perpendicular direction, there is a maximum power. And as I radiate, or I look at the radiation in angles that are shallower and shallower, then this radiation power becomes smaller and smaller, and actually goes to 0 at the angle 0. So here is angle theta, and this radiative power distribution follows a cosine law. That is important to remember also. This cosine law is called Lambert's law, and it's interesting to think about where it comes from. So I have this intuitive or solid state physics inspired thinking, that of course in a solid, let me draw the solid here, the radiation that reaches me when I'm looking perpendicular to it stems from a certain region of that solid. The solid not being transparent, it probably comes from a certain depth, that is also the absorption depth. If I radiate it onto the solid, light would be absorbed until a certain depth. So this depth says the region from which I receive the radiation that I observe. Now, if I observe from the side, the radiation that reaches my eye comes also from a certain depth. But that depth needs now to be measured in the oblique direction, because until it escapes from the solid, it has to cross a certain length. And so the components of the solid that contribute now to the amount of radiation reaching this detector here, or my eye here, is from a smaller volume. And that volume scales like the cosine of theta. That's my personal interpretation of Lambert's law. And I would say at this level, I stop here, and then we can continue tomorrow in the other lecture hall. Thank you for your attention and your presence. See you tomorrow. Bye-bye.